Okay, guys, this is what's going to be called video 3, but it's really kinematics review. And if you want to kind of follow along, this is topic. I set up these review units to all go in order of the topics in the book, right? So this is the beginning of topic 2, kinematics, right? Distance and displacement, speed and velocity, and so on. So, I just kind of work through this topic 2 through in the review unit. So if you're looking for extra help when we get to a particular topic you want to study, know that we are going through this chronologically. So this first series of stuff takes us up to page 34, basically. All right, basically takes us up to 30. Well, really to 33, and then it'll be forces, which is our next video, right? So I put making all the assignments in order of the blue book so you can follow along. So let's just quick talk about kinematics. It really all kind of starts off with the definition of average velocity or average speed. Two different things, right? Speed is not equal to velocity. They're not the same thing. Speed is a scalar, meaning it has no direction. We cannot represent it with a vector. Velocity is a vector quantity, right? We can represent velocity with a vector. Like, velocity is that way, has a certain magnitude, it has a certain angle, it's a vector quantity. All right, so average velocity, which also brings us the difference of displacement and time. Average speed, right, is distance traveled over time. And average, sorry for the handwriting, haven't done this in a while. So displacement over time. All right, distance over time, displacement over time. Now, what's the difference? Well, something, let's say it goes from point A to point B, and I have a classic story of, which I told you earlier in the year, about going hiking with my brother-in-law, and he was with a bunch of my friends, and we went on a hike, and there was supposed to be a beautiful lake at the other end. However, what happened was the sign here said 3 miles, right? And apparently the sign was made for people doing mountaineering, using compasses and doing backcountry hiking, so they could, they gave you the GPS, they gave you like a coordinate, and basically it tells you the distance, point-to-point distance from beginning to the end of the trail. And, so if you wanted to map it, you could figure out where the ending point was. Now, so the actual displacement here, which is the overall net change in position, was 3 miles. All right, so we set off on the hike, and it was a beautiful hike, but we weren't planning on being out that long, and it ended up being pretty darn long, and some of my friends were griping, and I was kind of the middleman, and I had to say, no, this would be great. And meanwhile, I'm thinking, oh boy, I hope this is great. Because my friends were not happy. And especially when over in this mark, we were like going along the edge of like a very marshy, swampy area. And the bugs were bad. But we probably actually walked more like 5 miles, which took a little longer than we were hoping for. So that was the distance we actually traveled. The distance we traveled was 5 miles. However, our net displacement from beginning to end was only 3 miles. So that took us, I don't remember how long, maybe an hour long hike or an hour and a half long hike. So let's say it was an hour, right? So our average velocity, the magnitude of our average velocity, was about 3 miles per hour, right? Our average speed was more like 5 miles per hour, which it must have taken more than an hour. 5 miles per hour is like jogging probably. But anyway, at the end, though, I will say there was this huge boulder, and it was beautiful clear water, and it was hot out, and it was an awesome swimming hole. I mean, it was just gorgeous. Nothing built up on the lake. It was in the Adirondacks. It was well worth the hike, but it really illustrated the difference between displacement and distance. Now, average velocity, average speed. Usually we do it in meters per second. No big deal. What if something accelerates, right? So a car accelerates from rest, reaches some velocity, gets faster as it's going, right? We say it has an acceleration, right? It's accelerating in the positive direction. Well, acceleration is defined as the change in velocity over time. It's the rate of change of velocity. And the units are meters per second each second. So when we drop something, right, it accelerates down at a rate of 9.8 meters per second every second. So that means every second the object falls for close to the Earth in the absence of air resistance, it picks up 9.8 meters per second of speed every second. All right, so that's the essence of acceleration, right? It's how much velocity is changing by each second. So if a car can accelerate at 20 meters per second, that means it starts off from rest at 1 second and be moving at 10 meters per second. All right, at 2 seconds it'd be at 20 meters per second. At 3 seconds it'd be at 30 meters per second. So really fast car here, right? 3 seconds up to about 60 miles per hour. Actually, that's probably not super fast, but not bad. All right, so every second, however much your velocity changes by every second, that's the acceleration. So we have these other equations, right? We have, okay, velocity, average velocity equals, they say distance, d over t. We have acceleration equals change in velocity over time. These are the way that they're written on the reference table, right? So this first unit, I'm just grabbing the reference table here. This first unit, we're basically dealing with these first 5 equations, right? D over t, delta v over t. The next one, v final. Well, if you put in v final minus v initial for delta t, and then you solve for v final, you get this equation, v final equals v initial plus at, right? If you think about y equals mx plus b, that is basically this, right? M is the slope of velocity versus time, is acceleration. Slope of v versus t is acceleration. The area under the graph is displacement, delta x, or I guess in Regent's world it's d. We usually would call it delta x. Next year we'll call it delta x, of course, in AP Physics. So really important there. So velocity, if it's a constant acceleration, it's just a nice linear velocity versus time graph. Area under the curve gives us the displacement, 1/2 base times height, all right? That brings us to our next equation, which is Al Grande, which is the area under this curve, equals d equals, I'll write it the way it's written on the reference table, v initial t plus 1/2 at squared. And on the final one is just a rearrangement of, you use a couple of these equations, put them together. Oh, there is one more. V final squared equals v initial squared plus 2ad. Now, I should say also, well, I'll come back to that in a second. There is one more equation that's not listed in the reference table, but is very useful. And it's the fact that average velocity can always be taken as the average of the initial and final velocity. That's super useful. And that's how you end up with this 2 in these equations, right? Using average velocity, putting average velocity into this equation, and then using acceleration to eliminate time or the final. It's kind of a fun little thing. So this is the timeless equation, or the v squared equation. We call this one Al Grande. That's just average velocity. So let's just look at an example really quick of a word problem, which are very common. We just these word problems have to be very quick, right? We've got to be able to do these very quickly, a word problem. Let's say let's do something kind of wacky. Let's say we have a car. Car moving at 15 meters per second, accelerates at a rate of positive, what did I say, 13 or 15? I'll say 15. My handwriting, I couldn't decipher. Positive 3.0 meters per second each second, or meters per second squared, for an R there, over a distance of 20 meters. Determine the final velocity. Determine VF. All right. Car already moving 15 meters per second, so it's moving pretty fast. It's going to accelerate. So it's going to move even faster. All right. It's going to pick up 3 meters per second each second over a distance of 20 meters. So I gave you a distance, not a time here. All right. So first thing I'm going to do is just kind of identify all my variables. I could use an organizational table, or I could just list them out. And I'm going to list them out over here, kind of on the side here, so then I can erase this and figure out which equation. So V initial is 15 meters per second. Acceleration, it's speeding up. It's positive 3.0 meters per second squared. And then the distance it did it over was 20 meters. We don't know time. We don't know VF. Now, all right. Now, there's another way of drawing this, right? Organizing this that I like to do as well sometimes. 1, 2, 3, 4, 5. V initial, V final, V average, acceleration, displacement, and time, right? So V initial is 15 meters per second. VF we don't know. V average we don't know. Acceleration plus 3.0 meters per second squared. Distance 20 meters. And so on. All right, so what do I do with this? Well, I don't know time. That's almost always the timeless equation. V final squared equals V initial squared plus 2AD. All right, I'm looking for V final, so that kind of works out. V initial, 15. I'm not going to put the units in here since I already listed them out multiple times. Plus 2 times 3 times 20. All right, so we got 15, and that's V final squared. Don't forget that, because you know that's going to be one of the wrong choices on the multiple choice question. Right? So I get V final squared equals 250. All right, so take the square root of both sides. I get V final equals 16 meters per second. So not that much faster, I guess. Kind of interesting. You know, so maybe that 20 meters, it just goes through by it so quick. It's already going at 15 meters per second. So that 20 meters, it's only there for probably less than a second across that 20 meters. So it hasn't gained much speed. I should have made that distance a little bit longer, but you get the idea. The last thing about kinematics that we should probably just quick talk about are the graphs, right? So X versus T, V versus T, and A versus T. Now, usually we write these vertically in class, but often the Regents makes them horizontal for some reason. So it's kind of beneficial to think about it, because some reason it is harder to think about these when you look at them horizontal rather than vertical. So position versus time. A linear position versus time graph means it's going the same distance each second, which is a constant velocity. And if the velocity is constant, that means there's no acceleration. All right, so then let's look at something that's accelerating. All right, so again, area under the curve, the slope of this is velocity. The slope of this is acceleration. The area under this is change in position. The area under this is change in velocity. All right, so that's kind of cool. There's no area under position versus time. We don't do anything with that. So velocity versus time, acceleration versus time. We should draw our velocity versus time and acceleration versus time graphs with positive and negative, because that is going to matter. All right. So something accelerating, it's curved. Slopometer, right? The slope of this line is getting steeper, so that means each time interval it's moving faster and faster. All right, so that's something with an increasing velocity and a positive constant acceleration. Area under the curve is displacement. Area under this is change in velocity. The slope of this is velocity, so that's not a constant slope. So you can really only look at the slope in little tangent lines, right? So in the beginning we have a very low speed, in the middle it's faster, and at the end it's very fast, right? So the slope of this is changing. The slope of this one is not changing, so it's a constant acceleration. The slope of this is 0, so the acceleration is constant. That's pretty much it for this unit. I'm not going to go any longer. There's plenty in your review book. I've lost my cap here. Plenty in your review book if you want a little more practice. Have a good one, guys. Study for a quiz tomorrow. It's going to be 5 questions, a combo of true and false, and multiple choice, okay? You've done a nice job. I'm going to, the points are easy on the homework. I'm not doing any partial credit or corrections for the quizzes, okay? All right. Talk to you later.